Hello, welcome to lesson 1.4. This is my housemate's cat, Mushi. Mushi, say hello. Oh, he wants to escape. Mushi, look at the camera. He's right there. He's right there. Alright, Mushi doesn't want to talk right now, but he usually loves to talk. I'm gonna let him out. There you go. Okay, that's your reward for tuning in this weekend to the video. Maybe we'll have more cat appearances in the future. Okay, so let's keep talking about function compositions. This video is going to be a little tricky because we're going to be discussing the domain and range of function compositions. And there's a lot of subtleties there to figuring out domains and ranges of function comps. So let's just start trying it. Okay, so you've got two functions, f and g. One thing that you'll always have is that when you combine them, say you do g inside of f, the domain of that composition must always be some subset, some part of the domain of g. So you're never going to be able to get more than the domain of g in this function composition, because the first function you're going to be plugging into, so if this is g, right, you're always going to be plugging your x's into the function g first. So if you're trying to plug something in and it's not in the domain of g, then you can't even do that. So that's the first piece to note, is that the domain of the composition is always some part of the domain of the inner function. So this is the inner function. Inner function. And then the, that's supposed to be a function. The domain, the range of f is, so the range of f of g of x is always a subset of the range of the outer function. So the outer function's range is going to kind of like contain the range of the function composition. And this is the outer function. Outer function. And why is that? Why is it that the outer function's range is always going to contain the composition's range? Well, it's because the last thing you're doing is you're applying f onto some number, and f has a range that you know based off of looking at f at its graph or at its equation. And there's no way you're going to be able to get answers that aren't in the range of f, because you're plugging things in to f, and so your answers are always going to be in the range of f somewhere. In this diagram on the right, it's supposed to illustrate these things. We have over here the domain is of the function composition is some chunk of the domain of g. It may be all of the domain of g, but it's never more than the domain of g. And so along the way, this x right here, you know, in order for it to make its way to the ultimate end goal, which is f of g of x, it has to pass into the domain of f. And so this output right here, this g of x, this output for that original x, since it lands in the domain of f, then we can actually have a home for it to go to. And so this is where it's going to end up, which is the range. So this is the range of f of g of x, which is, again, some subset of the range of f itself. To note the subtleties that are happening here, there's elements inside the domain of g that aren't in the domain of the composition, because where they end up after applying g is not in the domain of f. So when you try to plug them into the next function, they fail, so they don't work. Okay? So this x is out of the domain of the comp, out of f of f of g, fog. So it's out of the domain of the function composition. Okay, so that's the high-level view of what's going on. Our inputs are starting in the domain of the inner function, in this case g, and then they end up somewhere in the range of the outer function f. And along the way, they have to be going through the domain of f in order of the outer function in order for you to actually calculate the answer. All right, let's look at some examples and see how this works algebraically and graphically. All right, so how do you determine the domain of a composite function? There's kind of 3 steps that I follow to determine these domains. The first is I'm going to look at the rule for the composite function. So I'm going to determine the rule algebraically. So I'm going to plug the inner function into the outer function and come up with the rule for the composition. And then I'm going to look at that composition and see what its domain is. So from the composition's rule, usually you're able to identify, oh, I'm not allowed to plug in x equals 1, or I'm not allowed to plug in negative numbers, or whatever. So you should be able to see some domain from that rule. And then what you've got to do is, once you've looked at that, you combine what you know about the original inner function and the function, the domain that you just looked at. And you have to combine those into this into one set, which is the intersection, which is what's in both. So the intersection, this means this is what's in both. What is in both sets? What's in both sets? That's what's common. Okay. So we're looking at the inner functions domain, and we're looking at the domain that we determined from the composition rule, and then gluing them together into one domain, and that will be the domain of the composition. Okay, so that's pretty much it. That should get you there most of the time. All right, now let's go ahead and give it a try. So here's an example. We've got g of x is square root x, and f of x is x squared. Let's look at both f of g of x and g of f of x. So these are the two kinds of ways you can compose these. You can compose x squared into root x, or you can put root x into x squared, and then we'll have 2 different compositions. So let's first look at f of g of x. So the order of this is we're taking this function, which is g of x, and plugging it into this function, which is f of g of x, or f of x, okay? So let's first make an algebraic rule for f of g of x. So how do we do that? Well, we take g of x, the inner one, we replace it with what it is. So we're going to take this rule and replace that. Oops. Replace that. So that goes inside of our f function. And what's the f function do? Well, it squares things. So when you square the square root, you get what was inside of it. So this just gives you x, right? So by looking at that, you would say, well, from this function, I know it's a linear function, it's x. It would appear that the domain of the composition is all real numbers, right? Because you can plug anything into x. However, that would be wrong. That would be wrong because the first thing that you plug into is not, you don't plug it into x. That's a shortcut to find the answer. You're plugging your x's into g first, and we know what g is. So g is the square root function. And so if we think about what you're allowed to plug in, this is the domain of g. Dome of g. Well, you're only allowed to plug in numbers that are greater than or equal to 0, right? So that's our domain of g. And so then we get answers which are in the range of g the range. And these are, again, going to be numbers that are greater than or equal to 0 because they're answers to the square root function. And lastly, we'd be plugging those in. You know, here's the domain of x squared. Domain of x squared of f. And we can plug any of those numbers in because the domain of x squared is all real numbers, and we're going to get some answers out in the range of f. Range of f. And so these are going to ultimately be f of g of x answers. Right? So we started off. Where did we start? We started off with positive or zero numbers, positive numbers or 0. We ultimately ended up in the range, which is also positive or zero numbers. So our domain is from 0 to infinity. Because g's domain is from 0 to infinity, that's our inner function. That's the first thing we're plugging into. And that's the intersection, which is what's common between all real numbers, and the set from 0 to infinity is just the set from 0 to infinity. So that's our domain. All right, so that was a tricky one. It looks like our domain is all real numbers, but actually it's not. It's only numbers from 0 to infinity because g is the first function, and it has a restricted domain. Okay, let's look at another example. So the other composition. So working the other way, g of f of x, what's that going to look like? Well, let's determine our rule. What is g of f of x? Well, now we're plugging, I forgot my colors, but whatever. Now we're plugging f of x into g, right? So our function, our inner function is x squared, and our outer function is square root. So we're going to take x squared and plug that in to the g function. And what's the g function do? Well, it square roots things. And so this is something you may not have known, but the square root of x squared is not actually x. It's absolute value of x. And you think, oh man, when you square root a square, you're going to cancel the square and get what you started with. But here's the dealio. The square root is always a positive number. And so since g is giving you the positive square root, it's actually always going to give you a positive answer, no matter what x is. And so it's actually giving you an absolute value function. It's giving you what x is, but the positive version of x. So that's a trickery thing right here, but square root of x squared is not equal to x, as you might think. It's actually equal to absolute value of x. We'll see that on the graph in a little bit. So it would appear by looking at this, we know absolute value, it's good from left to right, that the domain is all real numbers. And now we have to decide, is that actually true? Well, it is, because the inner function f is x squared. So the inner function, remember this is x squared, and it has a domain of all real numbers. And all real numbers intersected with all real numbers, well, that's just all real numbers. It's what's common, and that's everything. And so the domain of g of f of x is all real numbers. All right, let's take a look at these graphically, and we should see those domains appearing on their graphs. Okay, let's get Desmos to load up. Zoom. Okay, so see we've got absolute root x up here and x squared right there. We're going to first look at f of g of x, which was the one where we're plugging the root into x squared, and we were like, hey, it's going to be all real numbers, but wait, it actually isn't. And wait, hold on, which is my order? Oops, sorry. The first one we did was g of f of x. That's where we're putting the root inside the square. So, sorry to confuse you, but we're putting the root inside the square. So this is g of root x. And look at that. It's x. it is the graph of y equals x, except it doesn't go to the left. It stops at 0. And so if you look at the domain of this, it's just going, you know, from 0 all the way to infinity. I think the cat wants to come in. So that's our graph for g of f of x. And so the domain is 0 to infinity, as we were saying earlier. It's not all real numbers. Now let's look at f of g of x. That's the absolute value function, as I was saying earlier. Remember, square root always gives you a positive answer. And so when you plug x squared into the square root, you're always going to get a positive answer out. And so that's why it looks like this v. And the domain is all real numbers, because any x you plug into g ultimately gives you a positive number. And so when you square it, or any x you plug into g, no matter what, positive or negative, gives you a positive answer. And so you're allowed to square root that answer. And so our domain is everything. So there's our domain. And you can also see from the graph the range is from 0 to infinity as well. Okay, let's look at another example. Boop, back to the top. Okay, sorry, not another example, but let's look at how do you find range of a composite function. So to determine the range of a composite, do the same kind of steps. You determine the rule for the composite algebraically. So you're going to look at the composite function, and then you're going to look at that and identify its range. So you'll try, you know, techniques we have for identifying ranges of functions, which is, you know, like, can you get any positive number? Can you get 0? Or can you get any negative number? What are the answers you're going to get from this function? And then the range of the composite is going to be the intersection, which is, again, what's common. So this is what's common. What's common between the range of the outer and the range of the rule that you determined, right? So whatever the outer function is, that range, you can't get more than that. That's the max. So because that's the last function you're plugging in. All right, so then let's try to actually determine the range of a composite algebraically. Okay, so here we've got a linear function, f of x equals x plus 3, and g of x equals x squared, which is a quadratic. Let's look at the ranges of both f of g of x and g of f of x. So f of g of x, we're going to plug g of x into f. So this function here is going in right there to the f function, which I'll highlight in green. So we're putting g, which is x squared, inside of f. And so what's that going to look like? So this x squared is getting plugged in. It's getting plugged in. Everywhere we see x in f of x, we're going to put an x squared instead. And so we have x squared plus 3 as the rule. So if you look at that rule, you're going to say, well, I know that's a parabola moved up 3, and so I know the range of it is going to be from 3 to infinity, right? That's where the vertex is. It's at 0, 3. And this would be correct, because the range of the outer function, what's the outer function? Let's look at it again. The range of the outer function is f. So it's x plus 3. What's its range? That's all real numbers, because it's a linear function. And so since f can give you any answer, when you do this composition, you're going to just be restricted down to whatever range you see. So, and this is a shorthand for intersection right here. This is intersection. It's the upside down U. Instead of what's saying in this set or that set, it's what's in both. And so the stuff that's all real numbers and 3 to infinity is just the stuff 3 to infinity. So that's our range. Okay, let's look at the other composition. Now we're going to plug f into g. So let me keep my colors right. So f of x was green in this example, and g of x was red. And so we're going to be plugging the f function x plus 3 into the g function, which is x squared. Okay, so let's see. So x plus 3 is here, x plus 3 is here, and so we are squaring x plus 3. So that gets you x plus 3 quantity squared, which I could FOIL, I could expand it, but from that I can see what the vertex is. The vertex is negative 3, 0, because it's a parabola moved to the left by 3. So it would appear that the range is from 0 to infinity, because it's a parabola sitting on the x-axis. And that's correct, because the range of g, remember the range of the composition is determined by the outer function. This guy's range is from 0 to infinity as well. And so you have the same ranges, so you're gonna end up getting all of that range of the outer function, g. So the range is from 0 to infinity. Let's go ahead and look at these two on Desmos and see their graphs play out. Okay, so we've got x plus 3 and x squared. So the first one we looked at was f of g of x, which was taking the parabola and ended up shifting it up 3. And you can see its range starts at 3 and goes up. And then g of f of x, which was plugging the linear function into the quadratic, that you end up shifting the parabola not up 3 but left 3, and we can see its range is from 0 to infinity, which is the same range as g of x, right? So you can kind of take a look and see that g of x's range, which goes from 0 to infinity, both the orange and the green graphs are going to be within this range, and this range, is from 0 to infinity. So no matter what actually f of x is, when you compose, really what we're interested in is this guy. No matter what f of x is, if you put it inside of g, you're never going to get something that's negative, because the last thing that g does is square things, and you always get a positive answer when you square something. Okay, alright, let's look at one last example and then we'll call it for this video. Okay, so now we've got two functions, 1 over 1 minus x and g of x equals square root x. Let's look at the domains for these two functions, for f of g of x and then the swap g of f of x. Okay, so starting with f of g of x, again, I like putting these colors in here so it's easy to see. We'll use red for g in this case and green for f, and so our outer function is f and our inner function is g. So we've got g on the inside, f on the outside, and so when we plug in this g function, keep it red, when we plug in this g function into f of x, we end up plugging in root x where we see x in f. So our new answer is 1 over 1 minus root x. If you look at this, it would appear, this is a tricky one to find the domain of. There's a couple of funky things happening. One is we've got a root going on. Well, no matter what, I can't plug in something that's, that's negative into this. And so I'm at least starting from 0. And then we've got a fraction too. And so if you think about the fraction, you can't divide by 0. So when would that happen? Well, that would happen if I plugged 1 in. So I'm not allowed to plug in 1. 1 is one of my numbers I can't plug in. And I'm not allowed to plug in anything negative. But it looks like everything else is fine. I can plug in numbers that are smaller than 1 or between 0 and 1. That's fine. 0 is fine as well. And I can plug in numbers larger than 1. So I just can't use 1 and I can't use negative numbers. And this would be a correct answer, because if you think about it, the domain of g is everything from 0 to infinity, right? The inner function, the red one, that's square root x, which is 0 to infinity. And 0 to 1, or 1 to infinity, is contained within that set of 0 to infinity. So this and this, if you intersect them, you get this set over here. This is what's common. On the number line, I'll just sketch it out for you so you can see it. This is 0, this is 1. You would open circle 1, close circle 0, everything in between there, and then everything to the right towards infinity. So the only x you're not allowed to plug in that's positive is 1. And then you're not allowed to plug in anything negative because you're trying to square root the thing. So that's our domain, 0 to 1, or union 1 to infinity. Okay, let's look at the reverse of this, g of f of x. So now we're plugging 1 over 1 minus x, which is the f function. So let me highlight g again. G is the outer one, and f of x is the inner one. So we're plugging f of x in, this guy is going inside the root, because g roots things, and so we're rooting whatever is inside of g. And so that ends up getting us root 1 over 1 minus x, which simplifies a little bit, and I'll leave it like this as 1 over root 1 minus x. And so it would appear, looking at this, that you can't plug in, and you can't plug 1 in, because 1 is going to give you 0 in the denominator, so that's not allowed. And if you tried to plug in numbers that were more than 1, you would end up getting a negative inside the root. For example, 2, right? Root 1 minus 2 is equal to root negative 1, and that's bad. So you couldn't plug 2 in, or 3, or 4, and so we want everything that's smaller than 1 not including. So that would be our domain, negative infinity to 1. And this would be correct because the domain of f is everything but 1, right? That's the only thing that's not allowed, because when you look at it, 1 over 1 minus x, plug in 1, you're dividing by 0. And so negative infinity to 1, not including 1, is just a subset. And so you're going to get this as your domain of the composition. Okay? Everything from negative infinity to 1, but not including 1. And let's look at that on a graph to see. Okay. So here's our f function, 1 over 1 minus x. If we plug the root in, we get this weird wonky graph, but you can see that we stop right at 0, and we zoom up towards some asymptote. Looks like we can get as close to 1 as we would like for our x's. See, we have 0.9 to 1, and if I keep going, I keep getting closer to 1. But not 1, there's an asymptote there, and we can get as close to 1 from the other side. Let's see that, 1.09, so it's getting closer and closer to 1. And then we have graph everywhere to the right of there. So this was our weird domain that was 0 to 1, not including 1, 1 to infinity, and that's the domain for f of g of x. The domain for g of f of x was the one where you said it was everything left of 1 was allowed. And you can see over here that we are 0.9, and as we go to the left, we can keep plugging in values. More and more values are fine over here as we go to the left. So those are our domains from the graphs and algebraically. Okay. I will see you guys on Monday, and maybe I'll have more kitties for you.